Bismillahirrahmanirrahim. Assalamu alaikum viewers. Welcome to my channel. And as you can see the topic, we are going to discuss today the mean value theorem and its geometrical interpretation exhaustively. You know that this theorem was presented by J.L. Lagrange, a French mathematician of 19th century. And he just explained that if you're having a certain function f which is continuous on a closed interval ab could be any real number, and it is differentiable on an open interval of your ab, means the boundary points are not included, then there's going to exist a certain point c belonging to this open interval such that this slope is going to be equal to the slope of the tangent line at the point C. Okay, so you can see that it is right exactly equal to the derivative of the function evaluated at point C. And as I have explained this thing quite deeply in my video of tangent line and derivatives, you can see in the description box, you can see the link over there. So you can easily trace that video if you want to have a look over there. So we are going to try to understand how this slope is going to be equal to the slope of the tangent line at this point C. Okay, so for this purpose, let us try to draw an arbitrary curve of a certain function f. And definitely this function is also arbitrary. Point A and B are also arbitrary. So we are trying to cover up this topic in a general way. So let us try to draw a figure in this respect. So here we go. Okay, so here we go, a curve. Like if you have selected a certain function and you just try to draw it, you just try to plot a graph of that function, you are going to have some kind of shape, and we just did that, and this is your function f of x. It could be any function, and you just try to draw its graph and you are having a curve like this. Curve could be of any shape, so I just selected this, a simple curve here. And over here we just maintain an interval of your AB, you can see, and in this way the corresponding y coordinate at this point A on x-axis, it's going to have a coordinate on y-axis right over here. And as you can see that the y-axis is actually interpreting the value of your f of x. Okay, so this point is going to be your f of a. Alright, it could be your y1, and this is your x1. Alright, in the same way, if you talk about this point B and it is your x2 for instance, then the corresponding y coordinate might be somewhere here. So let me try to draw it more clearly. And one hand is with the camera, one hand is with the scale. It's too difficult to handle this stuff. So let me try to draw this line. So here you go. So this point is actually your f of b. Alright, and this is your y2. I just named this point as my point A for my convenience, and let this point is your point B. Alright, so you see, once if I try to join these 2 points A and B, I'm going to have obviously a secant line, because a line segment joining 2 points of the curve is said to be a secant line, and I have just explained this thing quite in detail in my video of tangent line and derivatives. So let me try to join these 2 points A and B in order to get a secant line, and then I'm going to observe its slope over there. Okay, so this is the secant line AB, and I have to find out the slope of this secant line, and you can see that the slope of the secant line is actually the ratio of the distance covered on the x-axis to the distance covered on the y-axis. So once when you, and in simple words, primarily you can say that your slope is actually the ratio of your rise over run, right? And rise value you can evaluate by subtracting y2 minus y1, and that's how you get the value of your slope that you often interpret as your m. So you see the distance covered from this point to this point is your running process, and the distance covered from this point to this point is your rising process. Okay, so if I just try to join these 2 points, something like this. Let me use a different color in order to make a difference. I'm sorry, my ink simply spilled over here, but I hope you can cooperate with this. So how you're going to obtain this distance? When you subtract this whole distance from here to here, when you subtract this small distance from this big distance, you're going to have this distance, which is actually your x2 minus x1. So here you can see that my slope is, the value of my x2 over here is my b, and that of your x1 is my a. So x2 minus x1 is equals to b minus a. And in this way, if I talk about my rising length, it is actually the subtraction of your f of a from your f of b. Okay, so that's how you get this small portion value. So it is y2 is my f of b, my y1 is my f of a. I have already written over here as well. So that's how you get the slope of this secant line. Now the concept comes, if you are having a certain function which is very, very continuous within this closed interval AB, it is continuous from A to your B, there is no jump here. Plus, you can see that at any point within this interval, you can easily assign the rate of change. You can easily understand the rate of change, the behavior of the rate of change of this function within this interval, or excluding these points. All these points, at all these points, you can easily understand the rate of change, the behavior of the function, or the change that is happening in the behavior of the function. So it is differentiable, in other words. It is continuous, it is differentiable, then there should exist at least one point C within this interval such that the slope of the tangent line at this point of tangency should be exactly equal to this slope. That's what your mean value theorem says. So let us try to figure out, are we really having some point C over here which is satisfying this condition? So let us try to see that this is my secant line AB, this green one. If I try to slide my scale, you can see that this is the point over where I can draw this point. At this point, I can draw my tangent line having the same slope equal to this green line. Okay, so this is exactly the point. So let me draw a tangent line over here. So I just tried to maintain a line. You can see that, and you know that if the two lines are parallel, then they are going to have a same slope. This very preliminary concept of your analytic geometry. So you can see that this red line and this green line are parallel to each other. The difference between these two lines is only this, that this line AB is a secant line, and this line is just touching one point on this curve. So this is a tangent line. But both these lines are exactly parallel to each other. So whatever the slope you're having of the green line is the slope of this red line. So if you just try to trace the coordinates of this point of tangency, we just, it might be lying somewhere here. This is your C, we just call it C. And its corresponding y coordinate is, I'm just moving quite roughly, but I hope you can get it. This is your f of C. Okay, so this point is having x and y coordinates. This is the point, and this point C is lying within this interval, open interval. You know that once when we were discussing the tangent line and derivatives, I explained you that the slope of the tangent line explains the derivative of a function evaluated at this point. So derivative of a function is actually the slope of this tangent line. So my slope is also actually the derivative of this function at point C, or you can also write like this. Evaluate at point X and at point X equal to C. This is it. So both these values, both these lines are parallel. Whatever the value you're having this, the green line is also having the same value. So this was the green line formula. This was the slope of the green line, the secant line. It was for the secant line. This was the slope of the secant line, and this is the slope of your tangent line. And both these lines are parallel, so their slopes are therefore same. So in this way, the mean value theorem satisfies, and it says that if your function is continuous within this closed interval, differentiable within the open interval, then there is going to exist at least one point C belonging to this open interval which is going to satisfy this condition, and is satisfied. So the slope is of your f of b minus f of a is equivalent to your f dash c. So that's what your mean value theorem explains. So I hope this is clear to you. And there is another way of explaining or interpreting a mean value theorem, or expressing a mean value theorem, that instead of b, if I use a plus h, let me draw one more figure in this regards. I prefer to draw another figure, because if I just try to move on with the same old figure, it is going to mess that thing up. So that's why this is another figure. So you see, if you're having a curve of your function y is equals to f of x, a single variable function, this is the interval that we have just assigned here. This is your x1, this is your x2, and so on. The distance between these 2 points, if I just say that let it be from this point to this point, I just say let it be h. Okay, so you can see that the distance between these 2 points is b minus a is equal to your h. So you can replace your b by means of a plus h. Okay, you can use this representation. So in your theorem, you can also write like this, that if your function f is continuous on an open interval ab, you can also write like this, a or a plus h, and is differentiable on an open continuous on a closed interval, and differentiable on an open interval ab, you can also interpret it like this. All right, so there is going to exist a point C within this open interval a comma a plus h. So I'm going to now change the representation of my point C as well. So you know that this was your a, this was your b. I'm going to join, I'm going to get secant line. So this is your point C over here, whose slope of the tangent line is exactly equal to the slope of the secant line AB, and this was actually, that's what we did already in the first figure. So this point is lying over here. This is your point C. This is the location of your point C. So what is going to be the distance between these 2 points? Obviously it is going to be less than your h. So how about if we just try to represent C by means of a plus theta h. Now the question arises what exactly your theta is. So theta could be any proper fraction. Its value should lie between 0 and 1. Okay, So you know that whenever a proper fraction is going to be multiplied with any value, it is going to decrease that value. So suppose that if, for instance, if you should suppose that your h is your 5, for example, okay, this is your 2, this is your 6, all right. How can it be 5? It's going to be 4, all right. So c, for example, if it is lying over here, then c is going to be 2 plus, and theta, I just assume that let theta is going to be half, all right, and it's going to be multiplied with my h value. It's going to be 2, so it is 2 plus 2 give me 4, so this value is 4, all right. It is lying over here. So you can interpret your c by means of your a plus theta h, where theta is a proper fraction lying between 0 and 1. So you can interpret this theorem in this way as well, that there is going to exist a point c. At the place of your point c, you can write like this. You can write this. And there exists a certain point a plus theta h lying in this interval, open interval, such that f of a plus h minus f of a upon b minus a, which is actually your h, and it's going to be f dash a plus theta h. Okay, this is more accurate representation of your mean value theorem and more preferable. So how we have interpreted a b representation by a plus theta h representation, I hope it's clear. So let's move ahead and try to have a look on one example related to mean value theorem. Okay, so here you go, the example, and it is said that this is a function, and once if you just try to plot this function on a graphic calculator within this interval, you will see that it is going to give you a very smooth curve. And once a function is continuous, so also it is going to be it is also going to be very well defined with respect to its rate, in the respect of its rate of change behavior. So it is differentiable as well as continuous within this interval. It is continuous in this closed interval 1, 3, and it is differentiable in the open interval 1, 3. And there is going to exist some point c in the open interval of your, so given to us, such that f of b, here this is our b and this is our a, so f of b minus f of a upon b minus a should be equal to your f dash c. This is what your mean value theorem says, and we, in short, we write this. So our objective is to get the value of our c. Okay, the graphic calculator is going to authenticate you. If you just try to plot this function, it is going to satisfy that yes, it is continuous, and yes, it is differentiable as well. So we have to onward our work from this step. Let us try to find out our f of 3. My f of 3 is, to substitute 3 wherever we are having our x. Minus 2 is going to be 27 minus 9. So it is going to give me minus 8 here. Similarly, you just calculate your f of 1. And it is going to give you minus 2. Alright? But this is your f of b, this is your f of a, alright? And b minus a is obviously 2 here. Now let us try to differentiate this function with respect to our x. So once when we just differentiate our function with respect to our x, it is going to give us f dash x. So my f dash x, over here we are going to use the formula of our d by dx x power n, which is equal to your n times x power n minus 1. So this thing gives me 3x squared minus 5 times 2x plus 4. So my f dash x is 3x squared minus 10x plus 4. So in this way, if I just try to find my f dash c, if I have to replace my x by my c, it's going to be 3c squared minus 10c plus 4. So now I have to write this f dash c at this place, all right, and I would be able to find out my value of c in that way. So 3c squared minus 10c plus 4 f dash c is equal to my f of 3, which is minus 8, okay, which is my minus 8. F of 1 is my minus 2 upon b minus a is 2 here. So that's it. So minus 8 plus 2 upon 2 give you minus 6 upon 2, it's equals to minus 3. So this value is equal to your minus 3. And if I shift my minus 3 over here, it becomes plus 3 equals to 0. So my final equation comes out to be a quadratic, and it's this. All right. So you can either factorize, not factorization. I must say that you are going to use the quadratic formula here, which is going to be obtained like this. That okay. So once when you just here, your a is 3, your b is minus 10, your c is 7. It's a basic maths, and once when you substitute these values here, you're going to get 2 answers of the c. So let's just do it somewhere else because the page is finished. So I've just tried to maintain my c values here, and it's 10 plus minus under root 100 minus, it is going to be 84.6 16 on 6, and it's 4 upon 6. So you're going to have 2 answers of your c, which is 10 plus 4 upon 6. It's going to be 14 upon 6. On simplification, 7 by 3, which is 2.3333 and so on. So you can also write like this, 2.3 dot, showing that 3 is recurring here. And the second point is 10 minus 4 upon 6. So it is 6 upon 6 give you 1. And our interval was the open interval starting from 1, 3. So 1 cannot be the part of the open interval of 1, 3, because you know that in open interval the boundary points are not included. So c cannot be equal to 1. Yes, c is our 7 by 3 because it belongs to your open interval. So according to mean value theorem, c is going to be the point over which, if you just try to draw the tangent line, its slope will be exactly equal to the secant line so obtained by joining your 1 and 3, something like this. Okay, whatever the curve is going to be. This is going to be your 7 by 3. Okay, and this is just an idea. So that's how it looks like. So I hope you've understood. And if you feel that this video is really contributed a little bit at least in getting the concept, I humbly request you to subscribe my channel and hit on the like and hit on the bell icon so that you will be keep on getting new notifications from my channel. And I'm really thankful, my humble gratitude to all those people who have subscribed my channel up till now and who have liked my videos. So thank you very much. Take good care of yourself, and I'll see you in the future with more helpful videos, inshallah. But take good care of yourself. Allah Hafiz.